Alrighty, so what did we do yesterday? We talked about optimal codes, where, remember, a code is an encoding where we take input symbols, we map them to a sequence of output symbols, and we want these to be uniquely decodable so that we can still reconstruct the input from observing the output as one big long string together. And so we talked about optimal codes, which is where we minimize the expected length of the output. We say, well, we don't want to have more output than we really need. We want to keep that expected length minimal, where we have some view on the distribution of inputs, which is why we take an expected value. So we say there's some distribution of input symbols. We optimize the expected length of the output code word, and we showed that that expected length, no matter how we do it, if we have a uniquely decodable code, we can never do better than the entropy to base D, where D is the number of output symbols. We also saw that it was indeed possible to do better than the entropy of the input plus 1. We can always beat this. We didn't give a constructive argument, but we showed that this inequality must hold for the optimal code. We then said, well, the problem is this plus 1. This plus 1 gives us a bit of a headache. It's a gap on the right-hand side, which doesn't make us feel that great. So what we could do is, instead of encoding a single symbol, we encode a block of symbols. We take n symbols, treat them as one thing, encode them as a unit, as a block, and then we said, well, provided we have IID inputs, that allows us to basically turn this 1 into a 1 over n, where n is the length of the block. We then took a step back. We went back to Shannon's original argument, which showed, based on the asymptotic equipartition property, gave us some idea of what's going on here. He shows that what you're saying, the one way of constructing a good code, is you take the typical sequences, you say, those are the things I care about, I encode them pretty well in the same way for all the typical sequences. Then I take everything else and I just encode them crudely. And because we know most of the time we're going to be seeing typical sequences, that gives us a good calculation, a good expected code word length, if we do this. However, it's still not great. The problem is we still need to go and we need to compute these typical sequences, which is not so convenient. So Shannon was aware of this, and we'll come to an alternative construction of a code that he gives in just a moment. But first of all, I want to take a brief interlude to address this question here of IID. Because in the real world, we very, very rarely have IID sequences. That's a very boring class of sequences to talk about. So we have some things we can say about non-IID sequences. Now, this is not going to be examinable because I'm not going to prove the main result, which is this one, a theorem, which is the Shannon, Macmillan, and Bryman theorem. So what this says is, let x1, x2, etc. be an ergodic and stationary sequence. So what do I mean by these words? Well, stationary just means that each of these values, each of these random variables, has the same distribution. Okay, the distribution doesn't depend on time. In particular, it's stationary in that if I look at the pair doesn't have has the same distribution independent of time. So 1 and 2 have the same distribution as 2 and 3. 2 and 3 have the same distribution as 3 and 4. And similarly for triples, if I take any finite sequence, I can move that around, and I get the same distribution independent of where I look in time. That's what stationarity means. What about ergodic? Well, this is where I'm going to completely wave my hands and say ergodic means time averages converge to space averages. It's an old question. It comes from statistical mechanics. where you're saying that as time goes on, if I average out, I always get some sort of law of large numbers effect happening. Okay, so these assumptions are basically the minimal ones under which you get some nice law of large numbers. And we'll see examples of this later on. The key example that we're interested in most cases, is when these are the states of a Markov chain. If these are the states of a Markov chain under reasonable assumptions, then you can have ergodicity and you can have stationarity if you sample from the stationary distribution of the Markov chain. Okay, so if we have this, so if all states are able to go to all the others basically in some finite number of steps, and we have stationarity, then we're talking about that class of sequence. Well, if this is true, and we should say in a finite state space X. We're always talking about finite things here. Then minus 1 over n times the log of the probability, if I've got to look at the joint probability of x1 through to xn. Okay, so what have I got here? I've got n random variables. I look at the probability that I observe this particular sequence of n random variables. I evaluate that on the observations of the random variables. I then take a log and I divide by n and put a minus sign. This converges to, so it converges in probability to a quantity h bar as n goes to infinity. And what's h bar? Well, where h bar is the limit as n goes to infinity of 1 over n h of x1, x2, up to xn. So if this is the case, so you can think, let's just take a moment and check what happens if I have IID random variables. If I have IID random variables, then the entropy of the sequence of n of them is precisely n times the entropy of each. So that cancels that entropy, and I just have h bar is the entropy. And here what do I get? Well, the probability of a sequence is just the product of the probabilities, which is the log, means it turns it into a sum. We divide by n, we get an average, and we're just saying, law of large numbers, this converges to the entropy. What Shannon, Macmillan, and Bryman show is that if you have an ergodic and stationary sequence, this always happens. Why do we care about this? Well, it means that if I've got an ergodic and stationary sequence, I can still talk about this type of convergence. I can still talk about typical sequences, even though I don't have independence. So without independence, there's still a good notion of typical sequences, and we're going to get similar types of behavior to what we see in the IID case. We're not going to dwell on this anymore. We're going to come back to this later in the course where we actually start working with particularly Markov chains. We'll come back to understanding things of this type, but I thought it's worth mentioning now anyway. Okay, so with that interlude done, let's go back to thinking about codes. This is annoying. I don't actually like working with the AEP. I don't really want to enumerate things, so let's try and do it in a more clever way. Okay, so this leads us to Shannon's code. So Shannon said, okay, instead of going through the AEP, we can just use something similar to how we proved the Kraft-Macmillan, but it's not quite the same, as you'll see. What we do is we say, we assign an input x in x. So we're just thinking about how to deal with a single input. Okay, we're not dealing with a block. We're just going to apply this to a block if we want to, but we're going to construct a code explicitly. So we assign an input x to a code word, c of x, okay, of length. Okay, so what do we do? Well, we remember how we proved the Kraft-Macmillan inequality, and we said, well, we need enough digits, so it's minus log px of x. So if we'd sorted our inputs, we know that this is enough digits. Okay, if we've got a code word of this length, so this is the idea. So the recipe then, you first of all order the probabilities. Now that sounds easy. It is easy if I've got them all and I can store them all in memory and there's not too many of them. So that's step one. Step two is we define, in a decreasing way. So we order them so we've got the biggest probability comes first. So we order our symbols so that the symbol with the biggest probability is the first in our list. Then we define CS or CX as the first LX, which is minus log to the base. So we can do it in a generic output alphabet of probability of X digits. So this is how many digits we need to uniquely identify to make sure our code is prefix. Okay, in the size of y array expansion of the real number alpha x, which is equal to the sum I equals 1 to x take 1 p I. And this is basically the construction we used in the Kraft-Macmillan inequality. Okay, so because I'm not going to go through proving again that this is prefix. We already did that when we proved Kraft-Macmillan. So you've got ordered probabilities. Each time we get a number, we've identified a certain range that the possible outputs could be, and we've chosen enough digits that there can only ever be one code word in that interval that we've identified. So this is a prefix code. It is not generally optimal. It is not generally nice to compute. Why? That costs me n log n. If there's n inputs, that costs me n log n computations, order n log n, to do the sorting. And when n is large, that's a problem, and I've got to keep everything in memory, and I've got to have all these probabilities. So it's not always nice as a way of working. I also have to store the entire code. Because I've constructed this thing, I need to at least store the probabilities. If I store the probabilities, then I could reconstruct it if this ordering is unique. So if there's more than one way to order the probabilities, if I've got two probabilities that are the same, then this is not uniquely defined either. So you have to actually remember the entire construction, which is a pain when it comes to decoding because you've got to store the entire thing in memory. And so the total cost goes up because of this. Anyway, we can still say some useful things from it. So we can say one thing. So this is a little proposition. Let P and Q be PMFs. X be distributed like P. And Y a finite set with size of Y equals D. If we construct the Shannon code based on distribution Q. So the problem is, often I also don't know the probabilities. I might not know them exactly. So if I don't know them exactly, I might be constructing them based on something else, some other Q. How good is this going to be? Well, if I do this, then I get that h dx plus the divergence to base d of p against q is less than or equal to the expected code word length, which is less than hd of x plus the divergence to base d of p and q plus 1. And this is where the divergence comes in. We get a precise bound on how much worse we could be doing. Okay, the Shannon code gives us something which is at most 1 worse, so it does attain, it at least doesn't do worse than our upper bound that we've shown. Okay, on the optimal code, it might not be optimal, but it's not doing a lot worse. And even if I construct it with the wrong distribution, if this divergence isn't too big, then I get something that isn't too bad. Okay, so how do I prove this? So let's do it. We have, let's just calculate the expected code word length. So that's equal to the sum over x of px times, well, the code word length was minus log to the base d of qx, because I'm evaluating the expectation using p, but I constructed my code using q. There's that construction over there. I used q. I did it a little bit wrong. And so this is the expected code word length. Then this is less than the sum over x of, let's get rid of this ceiling. So minus log d of qx plus 1. So that's not so interesting. And then I'm going to try and mess with this a little bit to turn it into something that looks like a divergence. So this is x px minus log to the base d of, let's call it px, so I'll get rid of the log, px over qx times 1 over px plus 1. And you can see I've done absolutely nothing. Okay, so now that I have this, we can keep going. We use the log to split up that product, and we get this is equal to the sum of x px log to the base d of px over qx plus the sum of x of px minus log of px plus 1, which is equal to, we just read off what it is, it's exactly the divergence to the base d of p against q plus the entropy to the base d of x plus 1 as desired. Okay, so that's the upper bound. The lower bound follows by removing the plus 1. What do I mean? Well, if I didn't have a plus 1, I'd get the opposite inequality. I'd get it greater than or equal to, and the rest would follow through exactly the same way without the plus 1s everywhere. Happy? Okay, so that was Shannon's code. It's not so nice, so people then started thinking about this, and the next person to come along was Fano. So we get Fano's code, which was 1949. Okay, so Fano was thinking about this, and he suggested a different way of constructing a code, unlike Shannon. Fano's code, we'll see, isn't actually that useful because there's better things we can do in a minute, but it's worth understanding as a step along the way. It's very easy to implement. So given a PMF P on X, we'll say X is just a set 1 through to M, and X is distributed like P. All the other notation is as usual. What do we do? Step 1, sort the symbols. So P1 is greater than or equal to P2 is greater than or equal to PM. Okay, first step, same as Shannon, just sort everything so that it's decreasing. Because we know intuitively we have to put the shortest code words with the thing with highest probability. So that's why we're sorting. 2. Well, what we want to do, have you ever played the game Guess Who? Not guess, so the game with the little windows. You're trying to guess who it is. You know the optimal strategy for this, at least the one that reduces the number of steps, is you ask a yes or no question, so you want to cut out half of the options every time. You want with 50-50 probability to cut out some options. Actually, that's not the optimal strategy. There's a very cool paper that analyzes and finds the true optimal strategy, which boils down to if you are winning, do that, what we just described. If you are losing, take a risk. So you take a risk because that's the way you might get ahead, and you only care about winning the game, not about solving the game in the shortest number of steps. Anyway, so what we need to do, we want to say our first thing we need to do is to split the set of symbols into 2. Let's assume we're going for a binary code. Okay, so if we're doing a binary code, we're going to find R, which minimizes the sum I less than or equal to R, Pi, minus the sum I greater than R, Pi. So we're trying to find something which is close to halfway. Okay, you can see if we could do this perfectly, then this would have half the probability, this would have half the probability, and these two things would be equal. So we'd minimize it at 0. But maybe that's not possible. Let's try and minimize it. So we're going to find a split which gives us the best possible split between these two sets. Okay, and split into groups. X naught is the set of xi such that I is less than or equal to R, and x1, which is the set of xi such that I is greater than R. Step 3, define the first digit for entries in x naught to be 0 and 1 for x1. So this is the first output digit. Okay, so that's told me which of the two groups I'm in. That's the first question in Guess Who. And now what do? I repeat. I take each of these two groups and I go through and do this again. Sort everything out. Well, my probabilities are still sorted. Minimize the difference between the two groups, split it out, allocate another code word, another digit, so then it would be the second digit, and do a construction accordingly. So 4, repeat 2 and 3 until all code words are distinct. So everything gets separated out. Okay, so this is called the Fano code, or the Shannon-Fano code. As you can see, very early, 1949, just after Shannon. Again, not optimal. Really not optimal. But it's usually pretty good and fairly easy to construct. But now we get to Huffman codes. (1952). Well, Fano was teaching this, and Huffman was a student who went to Fano's lectures, is my understanding of the story, and chose to write a little project on improving codes. And what Huffman did is he realized that you could do it optimally. You could actually find an explicit, optimal construction. The way to think about this, Fano's algorithm is, in some sense, greedy. It says, what's the best first move I could do, not thinking about what happens after. So it's trying to just find a split which is somehow good initially, not thinking about, is that going to make it easier to split into the future. Huffman realized that optimization problems usually don't easily get solved this way. A better way is to go backwards from the end. You start with the richest problem, you solve all of those, you do backward induction, you construct something this way. So by solving in a backwards way rather than a forwards way, you get an optimal solution. Okay, now to do this, we're going to need a little bit of graph theory, and this proves quite useful. What we see is that this story here, the Guess Who game, it writes the code as a graph. You say the first digit tells me I'm in this group or that group. Okay? And the second digit then splits those two groups further. That looks like a tree. So we're going to need a little bit of definitions. Okay. So definition, an undirected graph, VE, so vertices, edges, okay, is a tuple consisting of a set V and a set of two element subsets of V cross B. Okay, so we have all of our nodes and we have our edges and edges between two nodes. So there we are. For V in V, the vertices, we denote by the degree of V the number of edges containing V. We call a graph DRE if the maximal degree of its vertices is D. And our interest is going to be D equals 2, principally. So these are binary trees where each vertex has two edges associated with it. I'll come back to this. I might need to clarify something. Okay. So let's define a subset of the graphs. Okay, definition. The set of rooted trees, T, is a subset of all graphs defined recursively by, first step, the graph tau containing a single vertex is a rooted tree, and 2, if tau I is in T for I equals 1 through to n, then the graph tau formed by adding a new vertex connected to the roots of Ti or T1 through to Tn is a rooted tree. Okay, this is not a great definition. I think this should probably actually be D+1 if we're going undirected. The reason is, okay, let's draw a picture. Everyone understands this thing when you draw a picture. What is a ternary tree? It's something where you have a root, the starting point, and you have at most 3 things coming out of it. And here I have at most 3 here, maybe I have 2 here, and 3 here. That is a ternary tree. It doesn't have to have 3 coming out, it has to have at most 3 coming out of each edge. Okay, we identify one of the nodes somehow as special, we call it the root. There we are. And so we have a root and everything that comes after it. The nice thing is when you've got the root, you can then define an ordering where this is the 0th layer, the 1st layer, the 2nd layer, etc., going through the tree. The final things, once you've done that, are called leaves. They're the leaves of the tree, and this is the root. So this is, we call it labeled if we label how many steps we are away from the root. So you can see this is this node here has labeled 2 because it's 2 steps from the root. And in fact, it wouldn't matter if I drew this in a different way, I would still have exactly the same structure. It doesn't depend on how I draw the tree here. Okay, why is this interesting for us? Well, we can think of our codes as being rooted trees. So if I had a code with 3 elements, 0, 1, 2, then I would have first digit 0, 1, and 2. And a second 0, 1, 2, let's say 0, 1, 0, 1, 2. And that means that each of these points, this has code word 0, 0. This has code word 0, 1, 0, 2, 1, 0, 1, 1, 2, 0, 2, 1, 2, 2. And so if I associate with each of these leaves a possible input, then the tree describes how the code works. And in fact, as soon as we have a prefix code, we know we always have a tree that represents the code. Okay, you have the tree because you've got the ordering given by how far you are from the root. The root defines which is the first digit you reveal, and then you just have a labeled tree of this sort. Is everyone clear from the picture, at least? Good. So claim there is a bijection from the set of DRE prefix codes to the set of labeled DRE rooted trees, whereby labeled I mean that every branch has a label which comes between 0, 1, 2, etc. Okay, so the main thing we're going to be doing is we're going to use this tree structure to analyze what's going on in our codes. Okay, we're going to describe just the binary version in detail. Once you've got the binary version, all the others are pretty obvious what you have to do. So, Huffman. Step 1, you do not need to order the probabilities. This is a great thing, except you've got to search them. So step 1, you construct a tree as follows. Step 1, combine the two least likely symbols. Okay, as 2 leaves in a tree. So what I'm doing is combining the 2 least likely symbols to create a tree, and then actually, rather than write the recipe up, I'll do an example and then I'll write the recipe up. You'll see what I'm doing as I just do an example. Okay, so let's think. What have I got? I've got, let's say x is equal to 1, 2, 3, 4, 5 probabilities. Okay, so x, 1, 2, 3, 4, 5. Let's have some numbers. Let's go 0.4, 0.1, 0.3, 0.05. What's left? 0.15. Everyone agree that's a distribution? I can do maths? Good. Okay. So here's our set of our distribution of values. So what are we going to do? We're going to combine the 2 least likely values. The 2 least likely values are this one and this one. Agreed? So now I'm going to combine those two, and I'll draw the picture as I go. So I'll have 2 and 4. Now I can remember what's the probability here. It was 0.1 and 0.05. So I'm going to add these 2 probabilities together. So that's going to give me something with 0.15 here. Okay, so if I think now I've combined these 2, I've now got a new element with 0.15. What's the next thing I do? Well, I combine the 2 least likely elements. 0.15, and my new object also is 0.15. So then I would have entry 5, which has 0.15, and I combine these, and that gives me 0.3. Okay, so I've now combined those. 0.3, next least likely is 3. So 3. And that's going to give me 0.6. And the only thing left is to add in 1. Okay, gives me probability 1, and I'm done. So that constructs a tree by combining these things in a nice hierarchical way. Okay, so how do I build a code? 1, 0, 1, 0, 1, 0, 1, 0. Doesn't matter how I label it, as long as I only use the numbers 0 and 1. That is a completely arbitrary choice. So that means 2 is encoded as 1, 1, 1, 1. 4 is encoded as 1, 1, 1, 0. 5 as 1, 1, 0. 3 as 1, 0. And 4 as 0. And you look at that and you go, yes, that is a prefix code. And that is the recipe. Let's do another simple example. So let's change these numbers a little bit. So let's go, so x, p, x. Let's do, so 1, 2, 3, 4, 5. Let's go 0.3, 0.2, 0.2, 0.2, 0.1. Agreed? Probability distribution again? Okay, so I'm going to do this a bit quicker this time. Okay, 1 and, I've got to choose one of these. Doesn't matter which one. Let's choose 4. 5, 4 combined. That gives me 0.3. Next two least likely, 3 and 4. Sorry, 2 and 3 rather. 2, 3 combined. There's there. And finally 1. That's 0.4. So actually I need to put the 1 here so I can combine here and there. So 1 1, 0, 1, 0, 0, 1, 0. And again, I could flip the zeros and the ones. It really doesn't matter. Okay, so what's the encoding? 1 is 1, 1. 5 is 1, 0, 1. 4 is 1, 0, 0. 2 is 0, 1. And 3 is 0, 0. There's the encoding. Happy? That is Huffman's algorithm. And you can see sometimes when I did this one, for example, the first step combines this and this, or I did it with 5 and 4. Why do I keep going to 5 and 2? So I combine these, which means that the next pair has to be here. And they're not overlapping. You don't get a simple code like this. Okay, there we are. That's Huffman's algorithm. Let's try and write the recipe out. Combine the two least likely symbols as two leaves in a tree. Build a new distribution on m-1 symbols where p prime 1 equals p1, p prime 2 equals p2 dot dot dot, up to p prime m minus 2 is p of m minus 2, p prime m minus 1 equals p m minus 1 plus pm. Because I've combined the two least likely symbols in my sequence. So I've just added their probabilities. 3. These are the two least likely symbols, or symbol probabilities. 3, repeat. That's the construction. So the interesting thing is this is a fairly simple construction. It's easy enough to do. We've just done 2 examples. But it turns out that this will always be optimal. So we can see that we are constructing the code tree from the bottom up. We're working with the least likely things first rather than the most likely things first. The algorithm, how long does it take? It takes precisely, so this algorithm takes size of x minus 1 steps. Okay, we know exactly how long it's going to take because at every step I combine precisely 2 things. I reduce the number of elements by 1. And once we've built the tree, we've just assigned zeros and ones to the branches. Now, that is an arbitrary choice. And you can also see in this example, I made the arbitrary choice to combine 5 and 4, not 5 and 3 or 5 and 2. All would have been perfectly sensible, Huffman consistent choices. What does that mean? It means that if you're going to use the Huffman algorithm, you have to remember the full construction. Or you need some other way of breaking symmetry. You need to have a rule. Always combine the 2 things with the largest values, or some other way so that you can reconstruct the Huffman code from it. And then you need a way of determining how you're assigning the ones and the zeros. If we have those things specified, so if all the probabilities are different, say, and we determine that you always associate the probabilities, or the ones and zeros in a particular way, then the Huffman code is unique. But in general, there's no guarantee of this. What happens if it's a D-ary code, if I'm not working with ones and zeros? Well, then I need to combine D things at each step. So if I'm encoding using 0, 1, and 2, I'm going to be combining 3 things, so I get a ternary tree. So I combine 3 things in every step, and I label them 0, 1, and 2. Same thing, same argument, same algorithm applies. Okay, why is it worth going through this? Well, proposition, let x and y be finite sets. P a BMF on X, and X a random variable distributed according to P. The Huffman code C, which maps X to Y star, is optimal. So when I say the Huffman code, I really should say a Huffman code, which is any code constructed using the Huffman algorithm, because there may be more than one. In fact, there's always more than one unless you tell me how to label the ones and the zeros in the tree. The Huffman code is optimal, i.e. if C prime is another UD, so uniquely decodable code, then the expected code word length under the Huffman algorithm is less than or equal to the expected length under whatever other UD code you seek to throw at it. So the Huffman code is prefix, clearly comes from a tree, and it is optimal, and it is easy to construct. Done. So the next step, which we're not going to get through fully today, is to try and prove this fact. So to prove the optimality, what do we need to do? Well, we need to prove some properties of codes, and in particular trees. So we'll start with this lemma. Let P be a PMF on X, X1 through to Xm, and assume, without loss of generality, P1 is greater than or equal to P2 greater than or equal to Pm for Pi equals probability of Xi. Then there is a prefix code which is optimal. That we've already proven. We already know there exists an optimal code which is prefix, but we're going to say some more about it. And any optimal prefix code satisfies. We're going to have three properties. One, Pj greater than Pk implies, so if the probability of j is greater than the probability of k, then the length of the code word associated with xj has to be less than or equal to the length of the code word associated with xk. So if you've got something that's more likely, it can never have a longer code word. Property 2, there are at least two longest code words. So there may be more than two, but there's at least two longest code words, so they have the same length, obviously, they're both longest. And three, two of the longest code words differ only in the last digit. In fact, we can say a little bit more, that any longest code word has another code word that differs only in the last digit from it. So they always come in pairs, which can only differ in the last digit. Okay? We call such a code canonical for P. So we won't go through the proof now, we don't have time, But I just point out that this is indeed true for the codes that we've constructed. So you can see here, okay, there are 2 longest code words, and they differ only in the last digit. In this example, there are 2 longest code words, and they differ only in the last digit. So this is generally true, that they're there, and you'll notice that the lengths of the code word are weakly ordered by the probabilities of the events. If I look at the events if I ordered these by probability, so 4, that's the smallest, so 4 has the longest code word. 2's next, so 2 has the longest code word as well. It's second longest, but it's the same length, but that's fine. Then 5, yes, 5 comes next. Then 3, yes, then 1. And so we get the ordering being weakly preserved. And similarly here, in this example, well, 5 and 4, so 5 has the longest code word, 4 is next, yes, these have the same, they're the same, and so you get a weak preservation of the ordering by the code word length. And so we see this coming out in the Huffman algorithm. And the next step is to prove that this is generically true, and it turns out that that's enough to prove that Huffman is indeed optimal. Okay, I'll see you next week.